This video lecture discusses using interrupts with UART receive. We're going to motivate the discussion with a very simple program. This program is going to input a string from the console, reverse it, and then output the reverse string. Let's see how this works in Bully Bootloader. Note that we have our pic24 program with this reverse string.c program, which is in chapter 10. I'm going to go ahead and send it a string, so I send it hello, and we see that we get back the reverse string. Let me go ahead and send one more string. Let's do that, and we see that we get the reverse string. Now let's do something different. I'm going to cycle power first. Let's send it a longer string. So we're going to send it a long string that consists of digits and lowercase alphabet from the file FIFO test_1. So let's use this mechanism to send that file. So I'll send that FIFO test one line.txt, which I've just done, and we can see that it reversed that string fine. Let's go ahead and now send it a file that has 2 lines in it. So we'll send it this one right here, FIFO test 2 line.txt. Let's do that. So FIFO test 2 line.txt. Let's do that. And now what's happened? Something different has happened. Here we started printing out the reverse string, and all of a sudden we got a software reset and a UART overrun error. Why did that occur? Recall that UART overrun error occurs whenever the input FIFO and the input shift register are both full and another character arrives. This can happen if the pic24 is off busy doing other work while characters are arriving. What's going on in this particular case? Well, a string arrived, the pic24 reversed it and began printing it out. Notice that it almost finished printing it out before a UART overrun error occurred. This is occurring because that second string is arriving while this string is being printed out. So the question is there anything that we can do to prevent this UART overrun error in this particular example? And the answer is yes. If we use a technique called interrupt-driven UART receive, then we can postpone this UART overrun error for a long time. So the problem is that we have a new string arriving while we're printing out the old string, and we need some way to buffer that new string until we're ready to process it. What we're going to do is we're going to use a software FIFO to store the incoming string, and we're going to use the UART receive interrupt service routine to do the read of the UART for us. Implementation of a software FIFO requires 3 things. It requires an array to hold data. Here we have an 8-element array. It also requires 2 pointers, and they're simply indexes, called the head and tail indexes. We're going to define a write operation to our FIFO as being to increment the head. So we'll increment the head first, and then we'll store data in the FIFO. We're going to define a read as being we're going to increment the tail and then read the data stored at the tail pointer. If the head index is equal to the tail index, then the buffer is empty. So this operation placed one piece of data into the buffer, here data A, and this operation here took one piece of data out of the buffer, data A. Notice that data is read in the same order as which it arrives. So after data A arrived and was placed into the buffer and then read, let's assume that other data arrives. So data B arrived, data C, data D, data E, data F, and data G, and now our head pointer is here. Let's say that one more piece of data arrives. Well, we're at the end of our buffer, so what we're going to do is going to wrap our head back to the beginning because we're at the end, and now data H is going to be placed in the buffer. At this point, if we try to place any more data into the buffer, then head becomes equal to tail, and we're going to get what is called buffer overflow. So if you ever do a write operation and head becomes equal to tail, that means that the buffer has overflowed. It also means that an 8-element buffer can only hold 8 minus 1 items, or in this case 7 items. It cannot hold 8 items, it can only hold 1 less than that, 7. This data structure is also sometimes called a circular buffer because of this action of the indexes wrapping back around to the beginning and simply circulating through these array locations. In our UART library code, we have implemented the software FIFO for UART1 receive interrupt. It can be turned on via this compiler flag, and I will demonstrate that in the example. So first of all, we're going to set the number of locations in the FIFO by this defined statement right here. Default value is 32. We're going to use an interrupt service routine, the UART1 interrupt service routine, to read characters when they're available, and we'll arbitrarily set a priority of 1 for this. Here's the array that's going to be for our FIFO. Here's our head pointer. Here's our tail pointer. This is going to be our new input character subroutine. Recall that before it was checking a special status bit in the UART1 status register to see if data was available. But now what this routine is going to do, it's simply going to check to see it's waiting for character to arrive. And what it means in this context is waiting for the interrupt service routine to actually put data into a buffer. So what it's going to do, it's going to wait in this loop right here while head is equal to tail. If head is equal to tail, that means that the buffer is empty, and it's simply going to loop here, waiting for the interrupt service routine to put data into it. Once head becomes not equal to a tail, then we need to read data out of the buffer. We're going to read data out of the buffer by first incrementing the tail pointer. So we're going to increment the tail pointer. We're going to see if we're at the end of the buffer. If we're at the end of the buffer, if this tail is equal to our FIFO size, then we need to wrap our pointer by setting it back equal to a 0. At this point, we can simply return this array element that's indexed by this tail pointer. So this subroutine waits for data to be placed into our FIFO by the UART RX interrupt service routine. When data gets placed in this FIFO, the head would no longer be equal to tail, and we take data out of the FIFO. So this takes data out of the FIFO. What puts data into the FIFO? Well, that's going to be the receive interrupt. If this is an interrupt is enabled, then when we receive a character, this ISR will be called. So the first thing that we're going to do in this subroutine is we're going to clear the UART1 RX interrupt flag. That'll be cleared to a 0. We're going to check to see if there's any errors. This is our error. This is the thing that's checking for a parity error, an overrun error, or a framing error. If none of those occur, then we'll go ahead and read the character out of the UART1 receive register stored in a temporary variable. We're then going to increment our head pointer. We're incrementing our head pointer because back here when we go to do a write, we increment head and then write data at that location. So we increment the head. We're going to check to see if our head is equal to our size of our array. If it is, then we need to wrap it back to 0. At this point, we're also going to check to see if head is equal to tail. If head is equal to tail, then we have the special condition of this condition right here where we've overflowed the buffer. So in that case, we're going to signal an error here. UART RX interrupt FIFO overrun. If that error condition does not occur, then all we need to do is place our character that we read out of our receive register into our receive FIFO array. This code is all defined in our library file pic24_uart.c. The interrupt-driven RX code is protected by this conditional compilation label UART1 RX interrupt. In order for this code to be compiled, you have to turn it on in the project, and to enable it, you go to Project, Build Options, Project, MPLAB C30, and add this preprocessor macro UART1 RX interrupt like I've done here, and that will cause this code to be included during project compilation and for your receive to be interrupt driven. If you ever want to change the FIFO size, all you have to do is just change this setting right here. If you want to change the interrupt priority, just change this value here. So does this fix the problem? Well, I programmed my PIC24 with the new reverse string, recompiled reverse string.c that has UART RX interrupt enabled. So let's go ahead and send our text file again. We'll send FIFO test 2-line. And we'll see that that worked just fine, no overrun. Let's send a few more lines. So we'll send the text file. This time we'll send 20 lines at a time. Let's do that. and that works fine as well. So this isn't going to totally prevent UART overrun. If I send an arbitrary long file, it will eventually overrun, but you can see that this is definitely postponing the problem for a long time. You can also do interrupt-driven transmit. This is useful if you have a large amount of data to send out the serial port. You can dump the data into a software FIFO and then have an interrupt service routine read data out of that software FIFO while the PIC24 does other work. This code is in the same library file as the receive-driven interrupt code and is protected by this conditional compilation label. The output FIFO is currently set to 32 with an interrupt priority of 1. This is going to be the array that's going to implement the output FIFO. This is going to be the head pointer and the tail pointer. The job of the outcar function is to write data to this software FIFO. It does this by first taking the head pointer and copying it to a temporary variable. We do this because the interrupt service routine is going to be looking at this head pointer in the background while we're actually manipulating it, and we don't want to manipulate it if the ISR routine is currently looking at it. So we're going to copy this to a temporary variable. We're then going to increment it and see if we're at the end of the buffer, and if we are, we're then going to wrap it. At this point, we need to see if this head pointer is equal to tail pointer. Recall that in this particular case, it would mean that that a write would overflow the buffer. So we can't write. We have to wait for the interrupt service routine to take data out of this buffer. So this is going to be a case in which our output software buffer is full, and we're going to loop here, waiting for these two pointers not to be equal. Eventually, the ISR will take a piece of data out of this buffer, and these will become not equal to each other. So at that point, we can take the character that was passed into the subroutine and write it to the output FIFO. We'll take our temporary pointer and copy into our head pointer. So now our head pointer is now updated. And at this point, we're going to enable our interrupt service routine. And what that's going to do by enabling the interrupt transmit service routine, that's going to allow it to take data out of this buffer. This is the ISR for the transmit interrupt. This is going to be called when the TX-IF flag is a 1. Well, when is it a 1? It's a 1 if there's any space whatsoever in the hardware buffer. Well, when you initially start up, it's empty, so this flag is going to be a 1, which is why initially when we start this code, this interrupt is actually disabled until we actually place data into the software FIFO. When we place data into a FIFO, we're now ready to start actually writing data out the serial port. So by setting this to a 1, the TX-IF flag is already a 1. That will automatically trigger the ISR. So once the ISR is triggered, what we're going to do is we're first going to check to see if the head is equal to tail. If that is so, then it means that we have totally emptied our software FIFO, and there's no more data to read from the software FIFO and write to the UART. So we would disable our interrupt service routine. If the software buffer is not empty, then we need to take something out of it. So we're going to increment the tail pointer. We'll see if it's equal to the size of the software FIFO. It is. We'll wrap it. We'll then clear the interrupt service flag, and we will write this piece of data that is sitting at the tail pointer location in our array to the transmit register. Let's be clear as to when this transmit interrupt flag is set. It is set to a 1 when a piece of data in this transmit register FIFO is transferred to the transmit shift register. When that occurs, that will imply that there's at least one free spot in this transmit FIFO. In that case, the flag is set to a 1. This interrupt is triggered. We read data out of our software FIFO and we write it to our transmit register. Meanwhile, the UART hardware is currently shifting out the data that's in the transmit shift register. There's a special case involved in setting of the TX-IF flag. When the UART module is first enabled, the TX-IF flag is set to a 1. This is needed such that when the very first character is written in out character to our empty software FIFO and we enable the transmit interrupt, we want that TX-IF flag to be initially a 1 such that the ISR will be called. When the ISR is called, that data will be taken out of the transmit FIFO and then written to our transmit register. the transmit register that's writing to is going to be this transmit FIFO. At that point, what's going to happen is the data in the transmit file that we just wrote is going to be immediately transferred to the transmit shift register, and the transmit flag will be set once again. That will actually trigger yet another interrupt, and then we'll detect that the head is equal to a tail, and we will disable ourselves. Meanwhile, we will be shifting data out of this transmit register, out this pin, and then we are free to call the out call routine again to dump more data into our software FIFO. Note that when we disabled ourselves in the case of our software FIFO being empty, we do not clear this transmit interrupt flag. We do not want it clear. We want it to be a 1, so that the next time we write to this empty FIFO and we enable this interrupt, then the fact that it's a 1 will then trigger the ISR to take data out of our software FIFO. Notice that there is no waiting by this ISR. Recall that we never want an ISR to wait for an event. If the software FIFO becomes empty, as indicated by head equal to tail, then it will simply disable itself, waiting for the out call routine to actually place data into this buffer. The only waiting that is done by the out call 1 routine is if when we increment the head pointer, if the head pointer becomes equal to a tail, then that means in this case that the buffer is full and we need the loop here waiting for the ISR to take data out of this software FIFO. We have talked about interrupt-driven techniques for both receive and transmit. Let's talk a little bit more about interrupt-driven receive. For serial port, receive and transmit typically operate at the same data rate. That would mean the input serial bandwidth is equal to the output serial bandwidth. When input serial data arrives, you have to add some non-zero processing time, which means the input bandwidth plus the processing time is greater than the output bandwidth. When you have this condition, if you have data arriving in a continual stream, then no matter how big this input software FIFO is, at some point it will overflow. So when will a software FIFO prevent overflow? It will prevent an overflow if data arrives in bursts, which is a more typical type of operation for a serial port. What you can do is you can size your software FIFO such that it is big enough to accommodate the largest burst of data, which will be dumped into your software FIFO by the ISR, and then when your CPU is free, it can then process that burst of data. Let's look at a sample problem involving a software FIFO. Here's a software FIFO with contents as shown and pointer values as shown. First question is, how many characters are currently in the buffer? Well, we know that there are characters in the buffer because head is not equal to tail. When we take data out of the buffer, we increment the tail, then read, so we're going to go 1, 2, 3, 4, 5, wrap back around, 6. Now tail would be equal to head, so there's going to be 6 characters in the buffer. What character is returned if the buffer is read? Well, the very first character that we would read when we increment the tail would be K, so that would be K. What location is modified if the buffer is written? Well, if we write the buffer, we're going to increment head and then write this location, so it's going to be location 1.